So we are starting looking at specific ligand-gated channels, and the one that we know the most about is the nicotinic acetylcholine receptor. And we know the most about that because it's one of the first ones that was found because it is located on the muscle. And so muscle was easy to observe and easy to do experiments on, as opposed to doing experiments on neurotransmitters and receptors in the brain. The muscle just had easier access. So we knew the most about the nicotinic acetylcholine receptor first. And one of the nice things is that building from the nicotinic acetylcholine receptor, we can build to at least very closely to two other receptor types, and then the last two that we're going to be talking about are relatively similar. So looking at what we already know about nicotinic acetylcholine receptors. And so as a nice review, right, are they ligand-gated channels or G-protein coupled receptors? How many subunits are available per channel or are necessary per channel? What is the nicotinic acetylcholine receptor permeable to? And then what is the transmembrane structure for each subunit? So just go ahead and try that, see if you remember it. And so pause the video, see if you remember it. For these, one thing that you can do is just, double click on this and then put the number in there for any ones that have question marks. This transmembrane structure you'll have to draw, but go ahead and give those a try. And hopefully what you're able to find is that you already know this. So they are ligand-gated channels, which I kind of already mentioned. For the nicotinic acetylcholine receptors, one thing you'll notice for these, there is the number 5 and there's the number 4. So for the nicotinic acetylcholine receptors, they need 5 subunits per channel. The transmembrane structure, you can draw it, but I'm also going to type here the transmembrane structure for each subunit. I think it looks like a W. So it has 4 transmembrane domains. And that looks like, just a quick, there's your membrane, and then 1, 2, 3, 4 W structure. Nicotinic acetylcholine receptor, always the same. And then for permeability, it is permeable to really all cations and selective for sodium. Ta-da! That's everything that we already know about that. So now let's move on and do things that we don't know yet. So what we said before is that, oh look, it has this transmembrane configuration. You need 5 of these individual subunits in order to make a channel. But now let's add some complexity in it. So one of the things is that different subunits for any given receptor can have small amino acid changes that are going to lead to slightly different subunits. And so for the nicotinic acetylcholine receptor, the muscle nicotinic acetylcholine receptor can have alpha, beta, gamma, and delta. So alpha, beta, gamma, delta, and then we also have nicotinic acetylcholine receptors in the brain, but they're made of different subunits. And so the muscle, since that was the first one that they discovered, these are all labeled number 1. And technically, the gamma and delta aren't one because they're the only. So it's just gamma and delta, but I put 1 here just to kind of make it easier. And then for nicotinic acetylcholine receptors in the brain, they are only made up of alpha or beta subunits, and you have multiple possibilities for these. And so one of the things for muscle, it's always the same. The configuration for nicotinic acetylcholine receptors at the muscle are always the same. Never changes. Well, there is a developmental difference, so I won't say never changes, but in adults, it is always the same. And how many subunits do we need for nicotinic acetylcholine receptors? 5, right? So for muscle and for neurons, The nicotinic acetylcholine receptors always have 5. So you'll notice here for the muscle, there's only 4 possible subunits. And all 4 are included, but there's actually 2 alpha. So add another alpha in here, and that will give you 5 subunits. Now, for the nicotinic acetylcholine receptors, they have many different possible subunit combinations. Those changes in subunit combinations can change the properties of the channel. So it can change the gating of the channel, like how fast or slow it opens or closes. The desensitization of the channel. So how other things can interact with it to basically desensitize or shut off the channel. Its inactivation. Its kinetics, so the speed at which it opens and closes, and then how they are localized at the postsynaptic membrane. So just some things can be changed because of the different subunit combination for individual channels. All right, so when we are thinking about nicotinic acetylcholine receptors, there are a couple of important structural principles, right? You need to remember that muscle's always the same, and that each nicotinic acetylcholine receptor needs that 5 subunits. And then, like I mentioned before, each nicotinic acetylcholine receptor also needs 2 alpha subunits. So the muscle, you take all these and you add in an extra alpha, you get 5. In the neuronal, you just need 2 alpha and then any combination. And the binding site for acetylcholine is on the alpha subunit. And in order to activate the nicotinic acetylcholine receptor, you have to have 2 acetylcholine molecules bind, and those binding sites are on the alpha subunit. So let's put that in practice. Knowing those things, build a model of a muscle nicotinic acetylcholine receptor and a neuronal nicotinic acetylcholine receptor. So go ahead and pause, and then you might have to duplicate some of these, but build one for the muscle and build one for that's available in neurons. And just remember, the properties are, if you haven't done it yet, remember the properties are that for each one you need 5 subunits, right? Those 5 subunits are going to form a circle, because they're gonna have to have a pore, so you can just put these post-its in a circle. The muscle is always the same, and neuronal are like mix and match, play however you want. So if you need more time, go ahead and pause and now do it. Okay, so now for the muscle, remember it is always going to be the same. So you basically just need all 4 of them. There is one little trick in that the gamma is in between the 2 alphas. There you go. So you've got your 2 alphas, you've got your 5 subunits, and in this one the gamma is in between the 2 alpha subunits. Now, for the nicotinic acetylcholine receptor, as long as you don't have any A1s in there, or alpha 1s, or beta 1s, right? You're really only working with these that are left. So as long as you have 5 subunits and 2 alphas, you can have any configuration that you want. Now, it might not be an actual one that exists, but it's a possibility, right? So here's the A7. There are ones that are known that have all A7s. As long as you have 2 alphas and then 5 total subunits. So we could do another one that has the A5. Let's put a couple of betas in there. You know, it may never have been found experimentally, but that means that doesn't mean it doesn't exist. So as long as we have 2 alphas and 5 total subunits, we can have whatever we want. And then I included these just so you have kind of the big picture. Remember that these are integral membrane protein subunits. So the subunit is going to look like this, but then each individual subunit is only 1/5 of a total channel. So then you're going to have this clumps together and is one tube here, either the alpha or the beta, right? But there are small amino acid changes that give them the different subunit types. And so this one, for embryonic muscle nicotinic acetylcholine receptors, there's a different subunit as opposed to the gamma. It's an epsilon instead of gamma, but this is what an adult muscle nicotinic acetylcholine receptor looks like. So you've got the two alphas, the gamma is in between the two alphas, and then the beta and delta are over here. For the brain, right, it's the same basic structure for each subunit, but again, different slight amino acid changes giving it the different subunits. And as long as you have two alphas, so this is homomeric, so it has the same alpha, so these are alpha 7s. This one's alpha 9, so maybe our book is a little bit out of date, but now you have a ninth subunit type. It happens. We find out new things. And then, what they're showing here, this little thing is where the acetylcholine binding site is. So there's, remember, two binding sites, each on the alpha. And then the red here is indicating the acetylcholine binding sites on the alpha. So as long as you have two acetylcholine binding sites, meaning you have two alpha subunits, and you have 5 total subunits, then you have a functional acetylcholine receptor. So a little bit more information about the functional properties of nicotinic acetylcholine receptors. So the second transmembrane domain of each of the subunits is what lines the pore. So if you have 5 subunits around, and the second transmembrane domain of each of those subunits is going to be what lines the pore. Just a quick view of what that actually looks like. So I think you might need a visual. So if you have that transmembrane, we kind of draw it straight across, but those transmembrane domains it's more of a clump, right? So you have TM1, TM2, TM3, and TM4 here, right? So TM2 lines the pore. So this is 1 subunit, this is 2 subunits, this is 3, 4, and 5 subunits. Each one of these right here is the second transmembrane domain of each subunit. And because of the amino acid sequence of that second transmembrane domain, now you have a ring of negatively charged amino acids at 3 different places around the pore, and those negatively charged amino acids are going to attract positively charged ions. So that's the sodium, potassium, and calcium. That's why it gives it the selectivity for cations, because it's got those negatively charged amino acid rings. And then in terms of opening, right, the acetylcholine binding in the alpha domain causes, or in the alpha subunit, causes the second transmembrane domain to rotate. So again, it's just a shape change. So the acetylcholine binds, changes the shape of the pore because it's rotating the second transmembrane domain for the subunits, so leading to pore opening. And then one final thing, this is just looking at how having the different subunits changes selectivity. So a lot of the nicotinic acetylcholine receptors are going to be selective for sodium, but the homodimer for the A7 is going to be more selective to calcium. And then the other one, I don't know why this is not, oh, I think I lost, there it is. So one that has a mix of alpha 4 and beta 2s is going to allow sodium and calcium through. So depending on what subunit composition, it can change which ions are actually moving through the channel.